Every so often, the idea of a giant space rock heading our way pops up.
Yeah, grabs the headlines for a bit.
Exactly. Maybe a close call in the news or a new disaster movie. It feels like a fleeting concern for most people.
Mm-hmm.
But if you're listening to this, you probably want to, well, dig a bit deeper. Understand the actual risks, what's really being done.
Right. Get beyond the surface level.
That's what we're doing today, a deep dive into asteroid impacts, but with a specific focus. We're looking at a fascinating period around the year 2000.
Ah, yes, and the Gaia mission's expected role back then.
Precisely. The surprising anticipation around Gaia for planetary defense. So our mission, if you will, is to get the core insights, understand the threat, the efforts to track it, why Gaia seemed like such a key piece, and, well, what happened next.
And we've got some good source material to work from.
We do, so let's jump in.
Okay, so it's easy to think of asteroid impacts as, like, pure Hollywood fantasy.
Right. Dinosaurs and Bruce Willis.
Sort of. But our planet's history, it tells a very different story. I mean, even right now, Earth is constantly being peppered by small stuff, meteoritic material.
Constantly. How much are we talking?
Estimates range from maybe 100,000 to 1,000,000 kilograms every single day.
1,000,000 kilos daily. Wow. Okay, but that's small stuff, right? Dust, pebbles.
Mostly, yes. Tiny particles burning up harmlessly in the atmosphere poses no real danger. But the thing is, larger impacts do happen, much rarer, obviously, but with potentially devastating consequences.
Okay, let's unpack that. Earth has actually been hit by big things before, like really big.
Oh, absolutely. I mean, go back to the very beginning. Earth itself formed through collisions, right? Smashing planetesimals together.
The solar system's construction phase.
Exactly. And the moon. The leading theory is it formed from the debris after a truly massive impact, a Mars-sized object hitting the early Earth.
Right, the Theia impact hypothesis.
Mm-hmm. And even after things settle down a bit, look at the moon's surface, all those craters. They're evidence of what's called the late heavy bombardment or terminal bombardment.
So the early solar system was just a really rough neighborhood.
You could say that. A cosmic demolition derby, like you said earlier.
Okay, so that's the ancient past.
Mhm.
What about, well, more recently in geological terms? Is there solid evidence of major impacts on Earth itself?
Oh, definitely. There's a resource called the Earth Impact Database. It catalogs confirmed impact structures.
What does it show? Any standout examples?
Well, you've got giants like Vredefort in South Africa and Sudbury in Canada. Both are incredibly old, around 2 billion years.
A billion. Okay.
Then, jumping forward quite a bit, there's Morakwang, also South Africa, maybe 145 million years ago. And of course, the famous one, Chicxulub in Mexico.
Ah, the dinosaur killer, 65 million years ago.
That's the one, widely linked to that mass extinction event. But there are others, too. Papagai in Russia, Chesapeake Bay under the water in the U.S., both around 35 million years ago. Even relatively recently, Karakul in Tajikistan, about 5 million years old.
That's quite a list. It really drives home that these aren't just theoretical possibilities.
Exactly. The key takeaway isn't just the names and dates. It's that significant impacts are a recurring geological process. They've shaped Earth's history. It's really not a question of if another big one will happen, but, when. Even if the timescales involved are immense.
Immense timescales,
Yeah.
okay. But anything more recent, something within human history or close to it?
Yes, definitely. The Tunguska event is a classic example. 1908, Siberia.
Right, I've heard of that. Flattened trees, but no crater.
Exactly. Probably an object maybe 50 meters across, exploding in the atmosphere before hitting the ground. It flattened something like 2,000 square kilometers of forest, a huge area.
Wow, from a 50-meter object.
And then much more recently and much better documented was the Chelyabinsk meteor in 2013.
Oh yeah, the dash cam videos were everywhere.
They were incredible. That object was estimated at only about 20 meters across, much smaller than Tunguska.
Only 20 meters.
Yeah, but the atmospheric explosion, the shock wave, it caused widespread damage, broken windows, structural damage, and hundreds of injuries, mostly from flying glass.
That really brings it home. Even relatively small objects can be dangerous.
It was a wake-up call for many. In fact, Dmitry Medvedev, the Russian prime minister at the time, specifically called for the international community to develop a global system to protect against these kinds of events. He used the term space guard.
A space guard system.
Okay.
That sounds proactive. Is that where this idea of near-Earth asteroids or NEOs really comes into focus?
Precisely. So NEOs, near-Earth asteroids. The technical definition is an asteroid whose orbit brings it within 1.3 astronomical units, or O, of the sun.
And 1 O is the Earth-Sun distance, right?
Yeah.
About 150 million kilometers.
Correct. So 1.3 OB is about 195 million kilometers. Still a vast distance, of course, but it means these objects are in our general orbital neighborhood, relatively speaking.
Okay. And are there many of them?
The number of known NEOs has exploded. Back in 1980, we only knew of a handful. By the year 2000, it was close to 1,000.
A big jump already.
And today, we're tracking over 25,000 known NEOs, and that number keeps growing as our detection capabilities improve.
25,000. Wow. Are they all dangerous?
No, not at all. Most are small, and most won't come anywhere near Earth. But within that group, there's a subset called PHOs, potentially hazardous objects.
Okay, what makes an asteroid potentially hazardous?
Two main criteria. First, its orbit has to intersect Earth's orbit, specifically coming within about 0.05 Lu, which is roughly 7.5 million kilometers.
Still sounds far, but cosmically close, I guess.
Relatively, yes. And the second criterion is size. It needs to be larger than about 140 meters in diameter. Below that size, while still potentially damaging, like Chelyabinsk, they aren't generally considered capable of causing, widespread regional or global catastrophe.
Right. So we're tracking thousands of NEOs, and a subset of those are PHOs, the ones we watch more closely. How do we rate the risk? Is there a system?
Yes, there are specific scales used for that. The Torino scale is probably the most well-known publicly. It runs from 0, meaning no hazard, up to 10, indicating a certain collision capable of global catastrophe.
Like a hurricane scale, but for asteroids.
Kind of, yeah. It combines the probability of impact with the potential consequences. There's also the Palermo Technical Impact Hazard Scale, which is a bit more complex and used more by scientists for detailed risk assessment.
Okay. And who's doing all this tracking? You mentioned Medvedev's Space Guard comment.
Well, the concept predates that, actually. There's been an international effort known as the Space Guard program, largely a collaboration between the U.S. through NASA and European bodies. Its goal has been to find and catalog these objects.
And how successful has it been?
Quite successful, especially regarding the biggest threats. NASA had a congressional mandate to find 90% of all NEOs larger than 1 kilometer in diameter by 2008.
The potential civilization enders.
Exactly. They actually met that goal, finding over 90% by 2011, slightly ahead of schedule if you account for the initial timeline adjustments. So by the early 2010s, we had a pretty good handle on the really big ones. The focus then shifted towards finding the smaller but still dangerous PHOs down to that 140-meter threshold.
That's reassuring, somewhat. So we knew about the risk. We were starting to track them. What made the year 2000 such a focal point in our story today?
It seems to have been a perfect storm, maybe not the best term, a confluence of factors. There had been some well-publicized near misses, asteroids passing relatively close to Earth. Public interest was definitely heightened. Movies might have played a role, too.
Armageddon. Deep impact.
Yeah.
Late 90s.
Right. So there was this backdrop of increased awareness, and then literally on the first working day of the new millennium, January 4th, 2000, the UK government made a significant announcement.
What was that?
Lord David Sainsbury, who was the UK's Minister for Science and Innovation at the time, unveiled a new government task force. Its specific job was to assess the risk posed by NEOs and figure out what the UK should do about it.
A government task force specifically for asteroid impacts back in 2000. That feels quite forward-thinking.
It was. It definitely signaled that this was being taken seriously at a high level, at least in the UK.
What was Sainsbury's reasoning?
Yeah.
Did he sound the alarm bells loudly?
His statement was quite measured, actually. He acknowledged the risk of a major impact was, and I quote, extremely remote. But, he added, it was still a risk that responsible governments could not ignore. He emphasized the need for better international monitoring.
A cautious but clear call for action.
Exactly. And this move was actually praised by Lembit Opik, who was a Liberal Democrat MP at the time.
Opik. The name sounds familiar in an astronomical context.
It should. His grandfather was Ernst Opik, a very famous Estonian astronomer who made significant contributions to understanding meteors and impact craters. Lembit Opik had been actively lobbying for government action on this issue. He called Sainsbury's announcement a brave political move.
Interesting family connection there. So who was on this Sainsbury panel? Who are the experts brought in?
It was a pretty high-powered group. Dr. Harry Atkinson, a physicist with experience in research and government science policy, Professor David Williams, who was the president of the Royal Astronomical Society then, and Sir Crispin Tickell, a very distinguished diplomat, former UK ambassador to the UN, known for his interest in environmental issues, including global risks.
A mix of scientific expertise and policy experience. What was their specific mission?
Their charge was basically to evaluate the nature and magnitude of the hazard from NEOs, and then recommend how the UK could best contribute to global efforts to detect them and, if necessary, mitigate the threat.
So, not just assess the risk, but figure out the UK's role in dealing with it.
Right. It wasn't just an academic exercise. They were looking for practical contributions. It really shows the level of seriousness around the turn of the millennium.
Was there much public engagement around this time? Or was it mostly government and scientists?
No, there was definitely public interest. There was even a competition launched seeking ideas from the public on how to detect asteroids or even deflect them if needed.
A public competition for deflection ideas. That's cool.
Yeah, trying to tap into wider ingenuity. And around the same time, other key figures were getting involved. Rusty Schweickart, for instance.
The Apollo astronaut, Apollo 9.
That's him, the lunar module pilot. He became very passionate about the asteroid threat. In 2002, just a couple of years later, he co-founded the B612 Foundation.
B612, like the Little Prince's asteroid.
Exactly. Their stated mission was, and still is, quite bold. Quote, to protect Earth from asteroid impacts. Schweikart was particularly interested in the role of space-based observations, specifically high-precision astrometry.
Astrometry measuring the positions and movements of stars and other objects very accurately.
Precisely. He saw that as key to getting the long-term predictions needed for any deflection effort. There's even an account from our source material of him meeting with scientists in 2002 discussing the potential of a specific mission, Gaia.
Ah, okay. So the threads are starting to come together. We have the Sainsbury panel assessing the risk, Schweikart advocating for solutions, and the Gaia mission developing in the background.
Exactly. The Sainsbury panel delivered its report on September 18, 2000. It contained 14 recommendations.
And did Gaia feature in those recommendations?
It did. Recommendation number 3 specifically highlighted the potential of ESA's upcoming Gaia mission. The panel noted it could make a significant contribution to surveying the NEO population.
So the official UK government report explicitly pointed to Gaia.
Yes. Meanwhile, Gaia itself was still, fighting for its place. It was competing against other mission proposals within ESA's science program, Horizon 2000 Plus.
A competitive process for these big science missions.
Very much so. But Gaia had strong science case across many areas of astrophysics, and this potential contribution to planetary defense likely didn't hurt. It went through rigorous reviews, and in October 2000, just a month after the Sainsbury report came out, Gaia was formally selected by ESA.
Perfect timing, it seems. What exactly was it about Gaia that made it so promising for finding and tracking asteroids beyond just being a powerful telescope?
It had several key design features. First, it was designed for onboard detection. It could identify moving objects against the background stars automatically as it scanned the sky.
So it wouldn't need humans constantly scanning the data for movers.
Right, a significant advantage. Second, it was incredibly sensitive, designed to observe very faint objects down to magnitude 20. That meant it could see smaller asteroids, or larger ones, much further away.
Okay, sensitive and automated.
Third, its scanning law meant it could make observations relatively close to the sun in the sky, an area notoriously difficult for ground-based telescopes because of glare. NEOs often hide there.
Filling a blind spot.
Exactly. And fourth, because of the way it repeatedly scanned the sky, it would observe the same object multiple times over its mission lifetime. Each observation would refine the orbit calculation.
Multiple precise observations over time.
Okay.
That's crucial for predicting where something will go, right?
Absolutely. And the initial predictions based on simulations were stunning. Gaia was expected to discover somewhere between 100,000 and maybe even 1 million new asteroids.
1 million new asteroids. That's incredible. Down to what sort of size?
The estimate suggested down to diameters of about 260 to 590 meters at a distance of 1 AO, so well within the PHO size range and beyond.
Okay, discovering them is one thing, but you mentioned Schweikart's interest in precision astrometry for prediction.
Yes, and this is where Gaia's original specifications were truly remarkable. The simulations weren't just about discovery numbers, they looked at orbital accuracy.
And what do they find?
They predicted that the orbital errors for asteroids discovered by Gaia calculated 100 years after the end of Gaia's 5-year mission. Those errors would be at least 30 times smaller than the errors you'd get from combining all past, present, and future ground-based observations over that same century.
Wait, let me process that. 30 times better than everything else combined. 100 years out.
That was the prediction based on the original design goals.
So put simply, Gaia could potentially tell us, with very high confidence, if a dangerous asteroid was going to hit Earth a century from now.
Essentially, yes. For asteroids large enough for Gaia to track with that precision, it offered the prospect of incredibly long-term, reliable warnings. 100 years is a lot of time to plan and execute a deflection mission, if one were needed.
That's a game changer for planetary defense, surely.
It certainly seemed that way. This potential was a major talking point. There was a high-profile meeting in Paris, May 2000, involving ESA, the European Southern Observatory, the European Science Foundation. They all endorsed Gaia, highlighting this unique capability for asteroid hazard assessment.
So the scientific community, the UK government panel, figures like Schweikart, everyone seemed aligned on Gaia's potential.
Yeah.
It sounds like the perfect solution was ready to go.
It really did look that way in late 2000. The stars seemed aligned, so to speak.
But I sense a but coming. If Gaia had this incredible capability, why isn't it the cornerstone of our planetary defense system today? What happened?
Well, this is where the story takes a turn. The initial target accuracy for Gaia's astrometry, the specification that underpinned those incredible 100-year predictions, was set at 10 micro-arcseconds for a star of 15th magnitude. That was the goal when it was selected in 2000.
10 micro-arcseconds. That sounds incredibly precise.
It is. Unimaginably small angles. But over the next few years, the mission went through what are known as D-scopes.
D-scopes, like reducing the scope.
Exactly. Reductions in the planned technical capabilities, often driven by budget pressures or technical challenges that emerged during development. Gaia underwent 3 significant D-scopes between its selection and around 2006.
3. And what was the impact on that crucial accuracy figure?
The cumulative effect of these D-scopes was that the final target accuracy was relaxed. It went from the original 10 micro-arcseconds down to about 25 micro-arcseconds by 2006.
Okay, 25 is still tiny, but it's more than double the original error margin.
Correct. And while the first D-scope might have had broader acceptance, our source material indicates that the project scientists at the time disagreed quite strongly with the necessity and impact of the latter 2 D-scopes.
Why? What was the concern?
The concern was that these further reductions, while perhaps solving short-term budget or technical issues, would significantly compromise some of Gaia's key science goals, including, critically, that unique ability to deliver those ultra-precise, century-long predictions for potentially hazardous asteroids.
So the very capability that the Sainsbury report highlighted and that got people like Schweikart so interested was directly impacted.
It appears so. The ability to predict orbits 100 years out with that 30 times better precision was linked to achieving that initial 10 micro-arcsecond goal. Relaxing the accuracy meant that while Gaia would still be fantastic at astrometry and still discover vast numbers of asteroids,
It wouldn't quite have that crystal ball clarity for the 100-year forecast.
that seems to be the consequence, yes.
Yeah.
The ultra-long-term, high-certainty warning potential was diminished. It could still provide valuable data, better than anything before it, but perhaps not the revolutionary, century-long guarantee that was initially envisioned for the most dangerous objects.
That must have been incredibly frustrating, especially given the timing. The Sainsbury panel points to Gaia, Gaia gets approved, and then its key capability for that specific recommendation gets diluted.
Yes, the source author expresses a clear sense of disappointment about this sequence of events. It felt like a missed opportunity. The political and public urgency around the asteroid threat, so strong in 2000, seemed to fade somewhat over the following years.
Other priorities took over, perhaps.
Perhaps budgets got tighter, technical realities set in, and so this specific aspect of Gaia's potential, the one that perfectly matched the Sainsbury panel's recommendation for long-term surveying, was quietly curtailed.
So to be clear, Gaia is still an amazing revolutionary mission, right? It's mapping the Milky Way in unprecedented detail.
Oh, absolutely. Its contributions to stellar astrophysics, galactic structure, fundamental physics are immense, and it is providing hugely valuable data on asteroids, too, discovering many refining orbits far better than we could before. No question about its overall success.
That specific promise from 2000, the 100-year PHO early warning system,
Yeah.
that particular capability isn't quite what was hoped for back then.
That appears to be the case. The later adjustments to the accuracy goals meant that while it helps significantly, it didn't fully deliver on that initial, very specific potential for ultra-long-term planetary defense warnings.
It's a fascinating story of potential, timing, and the complex realities of big science projects.
It is. And it's worth remembering, as the source points out, the underlying physics hasn't changed. High precision astrometry is still a powerful tool for this problem. Should the political will and funding reemerge with urgency, the method remains viable.
Okay, let's try and pull the threads together then. We've seen that Earth exists in a cosmic environment where impacts happen, from the constant rain of tiny particles to major historical events.
Right, it's an ongoing process, not just ancient history.
And around the year 2000, there was a real peak in awareness and concern, leading to official studies like the UK's Sainsbury report.
A moment where government and science seriously focused on the risk.
And right at that moment, the Gaia mission was coming into being, seemingly tailor-made, with its original specifications, to provide an unprecedented century-long warning system for potentially hazardous objects.
The potential was definitely seen as revolutionary for planetary defense.
But due to various factors, budget, technical challenges, the mission's accuracy goals were adjusted, which, while not crippling the mission overall, did reduce its ability to fully realize that specific ultra-long-term warning capability.
Exactly. A case of initial ambition meeting programmatic reality, perhaps. Gaia is still phenomenal, but that specific PHO forecasting aspect evolved.
It really highlights the long timelines involved, doesn't it? Both for the potential threats and for developing the means to detect and possibly counter them.
It absolutely does.
So here's a final thought for you, our listener, to ponder. We know that developing and deploying any kind of asteroid deflection technology could take decades. It requires sustained effort and funding.
A very long-term commitment.
But as we've seen, public attention and political will can fluctuate. What seemed urgent in 2000 might feel less so now, only to potentially become urgent again later. So given these long lead times and shifting priorities, what are the most effective long-term strategies for planetary defense? Is it about just continuously improving our detection and cataloging? Is it about proactively investing in deflection tech R&D even when there's no immediate specific threat identified? Or maybe some kind of international framework that can maintain focus regardless of national political cycles?
It's a complex balance.
It really makes you think about how we weigh these low-probability, high-consequence risks against all the other immediate challenges we face. How do we ensure long-term vigilance? Something to consider.